Okay, what's up, everybody? Welcome back. Today we're getting into chapter 6. We're talking about inner products and norms. We're going to add some geometry to our discussion. So let's start it off with a familiar friend, the dot product. We've all hopefully seen the dot product in our first course in linear algebra. So just a quick reminder, if you take x and y to be two vectors in Rn, the dot product of x and y, which we write as x dot y, hence dot product, is just the sum of the products of the entries of x and y. That is, if x is x1 through xn and y is y1 through yn, then x dot y is x1 times y1 plus x2 times y2 and so on all the way up to xn times yn. All right, here's kind of the idea to have in your head for all of this. So this is the motivation. So maybe not motivation, but just like an observation. So here, just think about this. Grab yourself good old-fashioned, say, R2, just for, visualization purposes. All right, here, I'm going to get a nice little line there. Okay, here. So let's suppose that this point right there is the point AB. That is, if you go straight down, then this is A on the x-axis, and if you go straight across, this is B on the y-axis. Yeah? All right, cool. What is this length L right here? Well, the length right there, L, is just B squared plus A squared's square root. That's L. Okay, but wait a second. Now, if this is, let's call this x, say, then notice, another way of writing this is that this is the square root of b times b plus a times a. Or another way of saying that is that this is the square root of x dot x. Oh, interesting. Okay. Similarly, think about this. This angle right here, this theta, what is that? So just think about regular old trig, like SOHCAHTOA for sine, cosine, and so on. Tangent, etc., right? Tangent is opposite over adjacent. So tangent of theta is opposite, which is b, over adjacent, which is a in this case, yeah? Something looking like that, okay. And so theta is equal to the inverse tangent of b over a. Yeah? So somehow, tied up in the coordinates of x, these a's and b's right here, you can discover the angle, you can discover the length. The length has a clear connection to the dot product, and later on, I'll show you that this angle theta has a clear connection to dot products as well. Our goal here, what we're going to do now, is we're going to try to take this kind of basic idea of saying, hey, look, length is related to the dot product, and we're going to try to generalize this to more things. That is, we're going to try to say, hey, what are the core properties of the dot product that make this thing here work? And then we're going to try to come up with a way to measure length using anything that satisfies the core properties of the dot product. That is, if we keep going, our next thing we're going to talk about is inner products. So the dot product is a type of inner product, or it is an example of an inner product. An inner product on a vector space V is a function that takes each ordered pair of elements of V to a number in the field. Here, we're going to take f to be R or C in particular. We'll just keep it simple. Okay. Which has the following properties. So this bracket notation is how we say inner product. An inner product, i.e. here, this thing, I'll put dots where you plug in stuff. This takes V cross V, ordered pairs of things in V, and sends it to the field. But it does so in a particular way. First off, it is positive, or at least non-negative. It says positivity. That's what your textbook calls it. I would call this non-negativity, since we only have greater than or equal to 0. But whatever you prefer to call it, it's essentially the same thing as long as you just define it in this way. In particular, it is greater than or equal to 0 for any v you throw in there. So you plug in the same argument to both things. You get something back that is at smallest 0. Also, it is definite. That is the only time you get back 0 is when, if and only if, that's the important piece right there, v is equal to 0. So combining, this says that v inner product v is greater than 0 for v not equal to 0. All right. The next condition you might suspect is something sort of like linearity. In particular, we're going to get additivity in the first slot. So u plus v comma w, that is if we take the inner product of the sum u plus v with w, then we get the inner product of u with w plus the inner product of v with w. That is, you can distribute the plus across the first slot in the inner product. Okay, cool. Similarly, you can do the same thing with scaling. You scale u by lambda, and you take the inner product of that with v. That is the same as scaling the inner product of u and v by lambda. Okay, so for fixed w and v, the function, I'll call it v maps to v comma w, is a linear, kind of cool, linear functional. Do you agree with this? That is, it's additive, it's homogeneous. All right, cool. So if you just look at that first slot and you fix something to go in the second slot, bada boom, you got yourself a linear functional. Or another way to look at this is that the map which sends w to this function is a map from v to the dual space of v. That'll actually turn out to be quite important, and we'll talk about that more later when we talk about representation theorems. That is, ways of saying, hey, when can I represent a linear functional as an inner product with a fixed element? So something that looks like this. Okay. And then finally, the last one, this has to do with our assumption here that f is r or f is c, the reals are the complex numbers. We have conjugate symmetry. That is, the inner product of u and v is equal to the conjugate of the inner product with v and u. Just a quick recall over here. For z equal to x plus iy in the complex plane, the conjugate of z is just equal to x minus iy in C, i.e., throw a minus on the imaginary part. Ugh, there we go. Tongue-tied. All right, so you just throw a minus on the imaginary part. That's what complex conjugation is. So this says that if you flip the order, you get the complex conjugate. And as a consequence, this is just symmetry if f is equal to c, since vu conjugate, or sorry, not if f is equal to c, I've written something silly right there. If f is equal to r, since vu conjugate is equal to v comma u in r, right? So if you take a number with a 0 imaginary part and you throw a minus in front of the 0, it doesn't change it at all, right? So if you conjugate a real number, you get back that real number. And so in the case that you're working over the reals, conjugate symmetry is just symmetry. It says that U inner product V is equal to V inner product U. Wow, what a long laundry list of definitions. Kind of reminds us of when we defined a vector space. So instead of stating all these definitions every time, let's just define an inner product space in the same way. An inner product space, it's just a vector space along with an inner product on that vector space. Nice. All right, cool. Let's prove facts about inner products. Let's get into it. All right, let's prove a bunch of facts about inner products. So let's just bang through this proof. It'll be fun. We're just going to get used to working with these bad boys. So first off, for each fixed v and v, the function that takes u in v to the inner product of u with v is a linear map from v to the field. So A, I claim that this is routine. So since I'll write v, or I'll u plus w, v is equal to uv plus w inner product v, and lambda u v is equal to lambda inner product of u with v, we are done. That is, this is a linear map. Okay, cool. So let's do part B. B says that if you put 0 in with any vector in an inner product, you get out 0 no matter what vector that was. This is true for any linear map. So we get B from A. That is, part A said that the map that sends U to U inner product V is a linear map. So if you put 0 in, you get back 0. That's obviously true for any linear map. Yeah? Okay, C. Now, C, maybe we have to do a little bit more work. This says that the opposite holds. That is, V comma 0 is equal to 0. Inner product of V with 0 is 0 for every V and V. Exact same thing here, except we flip the order around. Okay, now this is not too bad. Okay, so if we want to do this one, all we have to say is, hey, look, using conjugate symmetry, if I could write, does symmetry have two M's? It does, doesn't it? Using conjugate symmetry, v comma 0 is equal to 0 comma v conjugate, which is equal to 0 conjugate, which is 0. Okay, cool. Part D says that u inner product with v plus w is equal to uv plus uw. Oh, whoa. All right, this is nice. It says we have additivity in the second argument. Let's do this as well. Okay, so u comma v plus w, well, this is equal to the conjugate of v plus w u. I'm omitting the part where I say inner product every time. That is, the inner product of u with v plus w is equal to the conjugate of the inner product of v plus w with u. And now I'll just do my manipulation using this conjugate. So I'll get v inner product u plus w inner product u. And all of that is still conjugated since this thing is equal to that part. All right, and then I'm just going to split this conjugate up. Since conjugation is just throwing a minus sign on the complex part, you add stuff together, you're just throwing minus signs on each piece and putting it together. And now we just flip everything. Okay, uv, and I undo my conjugate, plus u comma w inner product. Bam. Nice. Not too bad. Okay, so we got it. We have additivity in the second argument. And finally, let's show that we have, something a little bit more interesting. U inner product with lambda v is the conjugate of lambda times the inner product of u with v. So this is not quite homogeneity. That is, I'm not just pulling lambda out, I'm conjugating lambda and pulling that out. Okay, so let's show it. Now u lambda v, I claim, is equal to lambda v comma u's inner product conjugated. This is just to reference, from this conjugate symmetry. We keep using that one, and now we're going to use homogeneity in the first slot. Okay, so just keeping my conjugate going, I get lambda v comma u inner product, and all of that's still conjugated, and this is equal to lambda's conjugate times the conjugate of v inner product u, which now I have lambda's conjugate times the inner product of u with v, undoing that using conjugate symmetry yet again. And bada boom, I've done it. We've done it. We're set. Not too bad. All right, so that's a pretty straightforward argument. Not awful at all, and I didn't even put anything else on this page since it's so short. So let's prove a few more things. Let's keep it going. Here, I'll just pop on over to the next page. Here is the next thing we're going to start to talk about, which is norms. So at the very beginning of all of this, we made a quick little reference to the fact that the dot product gives us some sort of a notion of length. That is, just looking at the R2 example, you could really quickly see that the length of that vector, that is how long the hypotenuse of this triangle is, was somehow given by the dot product. That is, the dot product just contains information about the coordinates of the vector. So if you take its dot product with itself, it contains information about the squares of the coordinates of the vector. Okay, not too bad. We know that squares have something to do with length a lot of the time, right? A squared plus b squared is c squared, something like that, yeah? We're going to use that fact now, and we're going to define a norm. So this is directly analogous to what we did with the dot product. So for a v and a normed vector space v, or in a, sorry, not a normed vector space, we're going to say an inner product space v. So a vector space v with an inner product, we can make v into a norm space, that is a space with a norm, that is a map defined as follows. So the norm of v, which we'll denote by v with double lines, kind of like absolute value, but it meant to denote the length of, is defined as follows. It is the square root of the inner product of v with itself, directly analogous to how we took the length here to be the square root of the dot product of x with itself. So we just generalized the properties of the dot product to an inner product. You should check and see that all of the things we said about inner products are true of dot products. And then we use the exact same logic here to define this thing called a norm. We'll see that it captures all of the notions of length that we want a measure of length to capture. For instance, here's a few basic properties. The norm of a vector is 0 if and only if that vector is 0. And the norm of a scalar multiple of a vector is the magnitude of that scalar times the norm of the vector. Okay, let's prove these guys. So this will just be a consequence of how we've defined the norm. So for part A, let's just think about it. What does it say? Well, it says that the norm of v is equal to 0. Well, that's true if and only if the square root of v inner product v is equal to 0. Well, this is true, of course. You take the square root of something and get back 0. That's true only if the thing inside the square root is equal to 0. But we know that this is true only when v is equal to 0. Right? Just going back to the very beginning, in our definition of an inner product, v comma v's the inner product of v with v is 0 if and only if v is 0. This is one of our properties for inner products. The inner product has to satisfy this definiteness property. So v is equal to 0 if V inner product V is equal to 0. Hey, look at that. Bada boom. Done. Nice. All right, what about part B? Well, let's take the norm of lambda V and just write out what it is. It is the square root of lambda V inner product lambda V. All right, and we can show what this is pretty straightforward, not too bad. We just get the square root of, well, I'll pull out one lambda from the first argument, and I'll get V comma lambda V. Okay, and now I'll conjugate really fast. So I'll get lambda conjugate of lambda V comma V. Use conjugate symmetry. Okay, and now I will get a lambda conjugate of V comma V conjugate. And then I will get, just flipping everything and using the conjugate, I will get lambda conjugate of V, since I just can flip those around and it looks the same, right? So I can get rid of that. All right, not too bad. But now, wait a second. What is lambda conjugate? So if Z is equal to X plus IY, then Z bar is equal to X minus IY. So Z bar is equal to what? Well, it's X plus IY times X minus IY. Let's multiply it out. X squared plus IYX minus IYX minus I squared Y squared. Well, hey, these two cancel out. I get an X squared. What is I squared? It's minus 1. So I get X squared plus Y squared. This is equal to the length, the modulus of that complex number, or sorry, not lambda, it's a Z here, squared. Oh, okay, wait a second. So this is the modulus of lambda squared, and then V comma V, but I can pull that out. And so I just get modulus lambda, square root, inner product of V with itself, but that's just how we defined the norm of V, right? It's the square root of the inner product of V with itself. So this is modulus lambda norm V, which is what we wanted to show in the first place. How about that? Nice. Cool. Okay, not too bad. Notice, if Z is a real number instead of a complex number, then this is just the absolute value of Z. So these bars here are just absolute value bars if lambda is a real number. If it's a complex number, then it is the modulus of lambda, the length of that complex number, treating it as a vector in R2. Okay, cool. So here is a nice little thing we can do with our notion of length here. I will draw you a little picture. All right. We can talk about orthogonality. That is, we can talk about right angles. So here is a nice little fact. I will show you this. We will use the law of cosines. So here's a fact. And I will describe orthogonality momentarily, but let me give you some motivation. V comma W is equal to the length of V times the length of W times cosine of theta. So the inner product of V and W is the product of their lengths times the cosine of theta, where here, what I mean by that is the following. So who really even cares what these vectors live in? In whatever vector space they live in, think of drawing them as some arrows. You know, turn the vector space, if it's finite dimensional, into Fn for some n. And then relative to just those two arrows, those two vectors, you can think of like the plane passing through them and bada boom, or a plane passing through them if it's not unique, maybe one of them 0. And bada boom, you've got a picture that looks like this with a V and a W. So here is my V, here's my W. All right. I've got an angle between them, some kind of a theta. This thing here, this length, is the norm of V, and this length here is the norm of W. All right. And then I have a little length right here. This length here is the length of v minus w. Yeah? Okay, cool. Nice, not too bad. So, using the law of cosines, we get that the norm of v minus w squared is equal to the norm of w squared plus the norm of v squared minus 2 norm v norm w cosine of theta. Do you agree with that? That is, law of cosine says, hey, if you've got a triangle that looks like basically like the same picture, you've got your C over here, you've got like an A here, you've got a B here, you've got a theta, then it says that C squared is equal to A squared plus B squared minus 2AB cosine theta. You might remember this from regular old trig. That's what this whole thing says. Law of cosine says that c squared is a squared plus b squared minus 2ab cosine theta. You've probably seen that in trig. If you haven't seen it before, okay, now you have. So recall or learn very quickly this fact. And just plugging in what our ab's and c's are over here, we get this nice identity. Then all we have to do is we have to expand this left-hand side and watch this. Okay, this just says that we have v minus w inner product with v minus w, since the norm squared is just the inner product of the thing with itself, right? The norm is the square root of the inner product of the thing with itself. So if we square that, we just get inner product of thing with itself. It's equal to this guy over here. I'll rewrite that momentarily. Let's see, actually, maybe I won't rewrite it. Maybe I can just do something fancy and do this. Oh, oops. Come on. There we go. Okay. Nice. All right, and now that I'm here, all I have to do is I have to modify this thing to work the way I want it to. Let's see what happens. Well, norm of v with w, or sorry, v with w, v minus w, inner product v minus w. I'll just expand everything out a little bit. It'll be kind of tedious to do so, but just going through and doing it, I will get, I promise you, the norm of v squared plus the norm of w squared minus 2 norm v comma w. And on the other side, we have this long thing right here. Okay, norm of v squared, norm of w squared, etc. And actually here, I can just do this. Boom, easy. All right, now all I have to do is go cancel, 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 divide by a minus 2, divide by a minus 2, and I get v comma w is equal to norm v norm w cosine of theta. Bam. So this fact right here comes from this manipulation. All right, cool. This motivates our definition of orthogonality. We'll say that two vectors u and v are called orthogonal if their inner product is 0. When do we get that using this fact right here for non-zero vectors v and w? Well, the only time that that happens, since the length of v and the length of w, their norms are non-zero if v and w are non-zero, is when the cosine of theta is 0. That is, they have to be at a, you guessed it, a right angle to each other. Yeah? Oh, okay. So using this happens when they're at a right angle. Okay, cool. Hopefully that made some sense. One little note I guess I'll throw on with this. this calculation assumes V and W are not scalar multiples of each other. That is, if they are, then we can't use the law of cosines quite like this. It's going to be a little bit of a mess right there. And in that case, it still ends up working. You just maybe have to do a tiny bit more work. It's an easier case. So think through it on your own if you don't quite believe that piece. This is not a result from your textbook. This is sometimes known as the I believe polarization identity, but it seemed like a useful thing to include just as motivation for this definition orthogonal right here. If you don't like it, don't think about it. Just say, hey, orthogonal means the inner product is 0. And let's move along to the next bit. All right, here we go. A little bit more. So up next, let's talk about orthogonality and what it gives us. First off, let's prove a few facts involving orthogonality and 0, since orthogonality is all about having an inner product of 0. So first piece, the 0 vector is orthogonal to every vector in V. Okay, part A, 0V equals 0 for all V in V by a previous result. That is, if we go back to what we just did, we got, here we go. 0V is 0 for every V in V. So one of the first things we proved about inner products. Bam. All right. We're all done. Nice. B. 0 is the only vector in V, so the only one that is orthogonal to itself. V comma V, inner product, equals 0 if and only if V equals 0 by the definiteness of the inner product. In fact, this is one of the things that we use to define inner products. If we go back to the definition of an inner product, this was definiteness. V comma V, the inner product there is 0 if and only if V is equal to 0. So 0 is the only vector that is orthogonal to itself. It's the only vector with length 0. Okay, cool. Let's prove the Pythagorean theorem using some of these facts and some other pieces of material we've covered so far. So the Pythagorean theorem says the following, that if u and v are orthogonal, then the norm of u plus v squared is equal to the norm of u squared plus the norm of v squared. Here's the idea of it. Draw, let me use nice lines. Here is u, here is v. Using the motivation that we talked about previously back over here with this whole v comma w inner product is norm v times norm w times cosine of theta, then this is well justified when we say orthogonal. We mean this. Okay, so here, this is a right angle. All right, and then if I draw right here, what is this? Well, all I have to do is I have to describe what this length is, right? What is it? This is the square root of u squared plus, or norm u squared plus norm v squared. Right? That's how long that is. It's the length of this thing. That's how long that is. Okay, so this is the Pythagorean theorem. Yeah? Just in the context of a normed vector space, a vector space with an inner product that we get a norm from. So, proof of it. Let's do it. It's not too bad, actually. Maybe this feels confusing, but I promise you, when you actually start to write it out, it's not terrible. So let's suppose that u and v are orthogonal. So suppose their inner product is 0. Then we get the following. The norm of u and v. I started writing it backwards. U plus v. It doesn't matter which way we do it, but there we go. The norm of u plus v squared is equal to u plus v, comma, u plus v in the inner product right there. Okay, not too bad. Just straight up definition, yeah. Let's split it out. All right, so we'll get u, comma, u plus v plus v, comma, u plus v using the additivity of the first slot. Now let's use additivity in the second slot. So I'll get u, comma, u plus u, comma, v plus, now additivity in the second slot for the second part, v, comma, u plus v, comma, v, bada boom. Let's just start writing this out right there. Now u and v, their inner product is 0. So I'll get the norm of u squared plus, and I'll write this one more time, uv plus u, comma, v conjugate, using conjugate symmetry, plus norm v squared. And since both of these guys are 0, I just get the norm of u squared plus 0's conjugate, which is also 0, plus norm of v squared. So this is just norm u squared plus norm v squared. Chapow. Nice. Okay, we're done. Easy. Not too bad. Pretty straightforward. Pythagorean theorem, all you got to do is just write out the definition of the norm of u plus v squared as an inner product, then just use the additivity of the inner product in both the first and second slot to pull it all down to this, then use one application of conjugate symmetry and our orthogonality assumption, and bada boom, you're there. Okay, cool. Let's keep it going. All right, so we've got a notion of orthogonality. This is a way of saying that two vectors are at a right angle to each other, so to speak. Here's the picture, basically, of what we're going to do here. So let's take a vector. Oops. Let me make this a nice line. So here, let me say, here's the idea of it, just to give this a nice section heading. Okay, I'll take a vector u right here, and then I will grab a vector, say like some v right here. All right. And in fact, let me make v a tiny bit longer and put it a little bit shallower, just to make this a little bit clearer so I don't end up drawing all over top of myself. If I take the nice right angle here, that goes right up to the tip right there, so that this is at a right angle. Notice I can grab, so this is v here, I can grab some little chunk here. Let me put this in a different color. This is CV for some scalar C, some scaling of V. Okay, some CV. And then I can get some other vector here. Let's call it W, is this vector right there. And what this says is that U is equal to CV plus W, with WV's inner product equal to 0, since they are at a right angle to each other. Oh, okay. So the nice idea here is that we can take a vector U, and relative to a vector V that's not equal to 0, we can break down U into a piece that lives in span V and a piece that is orthogonal to V. This piece here is W. Okay, so this is the orthogonal decomposition. Or I guess we could say, orthogonal decomposition is a good way to say this. So here's the idea. If U and V are in V, and V is not equal to 0, then if C is equal to the inner product of U and V over the length of V squared, and W is U minus that thing times V, then U is equal to CV plus W, and WV is equal to 0. So, really quick, let's just write this out. Now here, I'll say CV plus W Well, this is just, actually, let me even make this like a proof, let's call it, since we're making a claim. Okay, here's the proof. So we'll take CV plus W, and we'll write out what these things are. So this is UV over norm V squared times V plus W, which is U minus U inner product V over norm V squared V, which, wouldn't you know it, take this piece right here and this piece right here, they cancel out and you just get back U, right? One is negative the other one. Okay. So that is true. For sure, that is true. Similarly, W inner product V, well, this, we just have to write out what W is. This is U minus the inner product of U and V. Make sure that looks like a V. Over norm V squared times V, comma V. So I just replace W with what it's equal to from right up here. All right, and now I just will use a few properties of inner products. I will break this up really quick, and I will get U comma V minus inner product of U with V, which is just a scalar, over norm V squared times V comma V. But wait a second, what do I have here? I have U comma V minus, let's use linearity, so homogeneity in the first slot, U comma V over norm V squared, and then I have a V comma V, which, if you notice, is UV minus UV, and then I have a norm V squared over a norm V squared. So this is UV minus UV times 1. It's 0. Oh, okay. So we got that piece too. So W is indeed orthogonal to V. It is legitimately just this picture right here. Yeah, not too bad. We just had to figure out what the C is and what the W is. They have this nice form, and it's really easy to verify that everything works. All right, cool. Now, with this and with other things, we can do a very, very nice fact. So, this nice fact is one of the most important results anytime you're using inner product spaces. In the theory of inner product spaces, this one is a very important one. It is called the Cauchy-Schwarz inequality, although it is perhaps more rightly called the Cauchy-Bunyakovsky Schwarz inequality, in my opinion. Since a person who came up with this independently, actually, I believe before Cauchy and Schwarz, was Bunyakovsky, though it was not as open at the time period between Soviet mathematicians and other mathematicians. So whatever you want to call it, this is a very important fact. It says that the modulus of U comma V, inner product of U with V, is less than or equal to the norm of U times the norm of V. And this inequality is an equality only if and only if, one of U and V is a scalar multiple of the other. Okay, let's prove it. This is a very important fact, and it's really nice that it has such a simple proof. So, let's go for it. Now here's the idea of it. Let's say if, how about V? If V is equal to 0, then both sides of the inequality are 0, so it holds. That is, if V is equal to 0, then the inner product of U with V is equal to 0, and the norm of V is equal to 0. So 0 less than or equal to 0 definitely true. If not, then, in fact, maybe instead of making this v, let me make it u. This will actually make our argument slightly cleaner because I won't have to switch things and do a conjugation through the whole thing. Let's make it u. Notice, in that case, everything still holds the exact same way I said before, just norm of u is 0, and the inner product of 0 with v is 0 too. Okay, if not, then u is equal to, using this up here, cv plus w, where the inner product of w with v is equal to 0. So just using the orthogonal decomposition, inner product of w with v is 0, and u is equal to cv plus w. Okay. We can do this. All right. Using the Pythagorean theorem, we get the following. So just dropping really quickly back over here, the Pythagorean theorem says that for orthogonal vectors, the norm of their sum squared is equal to the sum of their squared norms. So going back over here, we'll just get the following. So the norm now of u squared, well, this is equal to the norm of cv plus w squared, which is equal to norm cv squared plus norm w squared, since this is just c times v comma w's inner product, and that's just 0 from here, right? Okay, but now all we have to do is do a little bit of manipulation. So up top, we got norm of cv squared. Well, let's write out what's going on here. We know what c is. C, in particular, was inner product of u with v over norm v squared. So I will get inner product of u with v over norm v squared. All of this will still be inside the norm times v, there, squared. And then I've got my w, that norm squared. And then I can pull this guy outside, right, at the cost of squaring it. And I will get a u comma v modulus of it squared. After all, when we started talking about norms, we said, hey, look, you've got lambda v. Take the norm of that. You get the magnitude of lambda, modulus of lambda, times the norm of v. Okay, cool. So just going back over here, I can take this thing and pull it out, and I will get that over the norm of v to the fourth times the norm of v squared plus the norm of w squared. Yeah? All right, nothing crazy. Nothing crazy so far. Now, all we have to do here is just make sure that everything works out nicely. So, just look really quick at what's going on. I'm going to get the inner product of uv squared over the norm of v squared plus norm of w squared. What do I want to show? That the inner product of u and with v is less than or equal to the product of the norm of u with norm of v. Blech, tongue-tied because there's too many different little things floating around. What I have right now is this. Norm of u squared is equal to this fraction here plus norm of w. And so I would claim that this thing is specifically going to be greater than or equal to I have too many bars on this top one. That's throwing me off. Sorry, guys. There we go. That's what was bothering me. Just this first part. If I'm summing two things together and the smallest they can be is 0, then take one of them away, right? Summing two non-negative quantities together. Ugh. Lag on my drawing tablet right there. So, norm u squared greater than or equal to modulus of u comma v squared over norm v squared, and u is norm squared, norm v squared is greater than or equal to u comma v's inner product and absolute value squared. Or, saying it another way, it's the result we want. Let's just write this backwards. U, forgot an inner product bar, or the inner product of u with v's absolute value is less than or equal to norm u times norm v. That is square root both sides. Bada boom. You're done. Not bad. So everything's equality up to this last line right here where I say just get rid of the w. Not terrible. So what does that mean? When is this an equality? Well, the only time it's an equality is when this norm of w is 0. And what that says is that when you take u and you break it down into a part that lies in the span of v and a part that is orthogonal to v, then the part that's orthogonal to v is 0. That is, u is equal to cv. So that's the claim we had right up here. Equality if and only if one of u and v is a scalar multiple of the other. Oh, so if u is equal to cv. Oh, cool, nice. Notice here, we have to say that indeed v is non-zero. So so I guess maybe that is something I'm being not clear on. If both u and v are equal to 0, then obviously this is true. If one of them is not, then you can cover the case where that one is the v here. All right, cool. So maybe I skipped over the kind of trivial case where both of them are 0, and I'm assuming now that v is non-zero in this proof. But that little tiny detail aside, not a terrible proof of the Cauchy-Schwarz inequality, which says that the inner product of u and v in absolute value is less than or equal to the norm of u times the norm of v. Another easier proof of this, if you want, just goes back to what we did here with the polarization identity, where the inner product of v with w is norm v, norm w, cosine theta. Cosine of theta is less than or equal to 1. Yeah? So, absolute value of this is equal to norm v, norm w, absolute value of cosine of theta, which is certainly less than or equal to norm v times norm w. So that is actually a much faster proof than this longer one we just did using an orthogonal decomposition. So pick the one you like the most. Let's keep it going. All right, last little bit. Let's finish strong. So here we go. Triangle inequality. Let's suppose that u and v are vectors in an inner product space. Our claim here is that the norm of u plus v is less than or equal to the norm of u plus the norm of v, with equality if and only if one of u and v is a non-negative real multiple of the other. Okay, kind of wild. Let's go through the proof here. This is not actually a terrible one. This is a useful one. So, start out just with what we want. We got the norm of u plus v, and what we're going to do is we're going to square it. All right. Now, if we square it, it'll make it a little bit easier to work with. I won't have to use as many square roots and everything like that. Let's just write what this is. This is u plus v, inner product with u plus v. All right. Split it up using the same kind of technique we've used so far. I'll get u, inner product with u, plus, just going on through right there, I will get a u inner product with v. Then I will get a v inner product with u, and I will get a v inner product with v. Okay, so splitting it up, first in the first argument, then in the second argument. Nothing too bad. Okay, now put it all together. I have a norm of u squared right there. Then I have a norm of v squared at the very end. So norm u squared right there, norm v squared right there. And then I have a u inner product with v. And then I have a, now I'll do a conjugation, u inner product with v conjugate, since if I want to flip those guys, I have to conjugate. Now, just an aside really quick, if z is equal to x plus iy, and z bar, the conjugate, is equal to x minus iy, z plus z bar is just equal to 2x, i.e. z plus z bar equals 2 times the real part, which we'll write as re z, 2 times the real part of z. So this just turns into the norm of u squared plus the norm of v squared plus 2 times the real part of uv inner product. All right, nothing too crazy so far. I claim that this is less than or equal to the norm of u squared plus the norm of v squared plus 2 times the magnitude of v comma w. Okay, so 2x, I claim, is certainly less than the magnitude of this guy, right? So magnitude of z is x squared plus y squared. And I claim that this is definitely greater than or equal to x squared, right? Okay, so just throw 2's in here. Yeah. Which, in this case, will certainly be bigger than just getting tongue-tied. Sorry about that. So 2 modulus of this thing bigger than that, which is certainly bigger than, it's going to be, yeah. Two times the real part. Okay, cool. We're all good right there. Everything's fine so far. And now, all we're going to do is we're going to use Cauchy-Schwarz. So, norm u squared plus norm v squared, just taking it from the previous line. Now, modulus of v inner product w, we can say is less than norm v times norm w, right? That's what Cauchy-Schwarz said on the previous page right there. Norm of the inner product of u, magnitude of the inner product of u and v is less than or equal to norm of u times norm of v. Bam. Look at that. We're right here. Okay. So via the Cauchy-Schwarz inequality, we get right there. Okay, everything's looking pretty good. And this bad boy right here is not too terrible. Why? Well, now that we're looking at this, hey, check this out. Is this just equal to the norm of u plus the norm of v squared? That is, if I multiply this out, norm of u plus norm of v times norm of u plus norm of v, I'll get a norm of u squared and norm of v squared, and I'll get 2 norm v times norm u. I don't know why I wrote a w somewhere in here. I wrote a W right there. Sorry, that should be a U. I hope I didn't throw anyone off by that. That W should be a U. I'm getting my U's and W's mixed up. Sorry about that, guys. Okay, there we go. So nothing terrible. All right. And wouldn't you know it, we get our desired result. So norm of U plus V squared less than or equal to norm U plus norm V, that whole quantity squared, and just taking a square root, norm of U plus V is less than or equal to, and I don't even need this parenthesis anymore, it's just the norm of U plus the norm of V. All right, not too bad. Not too bad. If you want to verify that equality holds if and only if one of U and V is a non-negative real multiple of the other, all you have to do is look at these two steps right here. When we used these two things, Cauchy-Schwarz is an equality precisely when one is a scalar multiple of the other, and the real part of UV's inner product is equal to just the getting confused to the whole inner product precisely when one is a real multiple of the other. So perhaps this is a little bit pedantic right there. If you want to go through and verify that, that is a good exercise. But let's finish off by doing just one last very short inequality that is, or equality actually, that is very nice and good to use. So I'll prove it really quick, then I'll draw a picture. This is called the parallelogram equality. It says that for U and V and a inner product space V, then the norm of U plus V squared plus the norm of U minus V squared is equal to 2 times the quantity of the norm of U squared plus the norm of V squared. Sounds complicated. It's not if you draw the picture. Let me give you the proof first. So, norm U plus V squared plus norm U minus V squared. Well, this is just equal to the inner product of U plus V, U plus V, plus U minus V, U minus V inner product. Okay, all I have to do is expand everything out. I will get U plus U V plus VU plus VV from this first one. And then from the next one, I will get plus a, now I just have to write everything down again. Okay, I will get UU, and then I will get a, and now I'm breaking everything up here, minus UV, and then I will get minus VU, and then because I'll get two minus signs canceling each other out right there, I will get a VV. Yeah? Okay, so I can go cancel, cancel, VU minus there. Okay, what do you know? I have a 2 UU, and I have a plus 2 VV inner product. That's all that's left over. So I can pull that out, and I get a 2 norm U squared plus norm V squared. And that's just what I wanted right here. Nice. Here's the picture of it. All you have to do is draw a parallelogram. Okay. Okay, so here is my U, and here is my V. Okay, now I take my V and I just translate it along right up here. Okay, then I have another copy of V over here. Take another copy of U down here, and you can see what's going on. If I go all the way up to right here, this is the vector U plus V. And if I go down right here, this is the vector U minus V. So all I'm doing is saying, hey, what's the length of this one? And what's the length of that one? Well, I can calculate it using, you guessed it, I can use the law of cosines, use it 2 times, and I can get back to this result. Or I can do this maybe nicer and easier manipulation right there, but boy, can't you tell it. These two guys, you put them together, and their lengths together are equal to 2 times the lengths of these pieces right here. So that is 2 times those lengths. All right, cool. Neat. So hopefully that helps a little bit. Hopefully that's a good introduction to all of the nice different things you can start to get from inner products and norms induced from them. We will talk a ton more about all of the nice structure that having an inner product gives you and all of the wonderful things it lets you say. And we'll do that next time. So have a great day. See you later.